This is Gyroscopic Precession Part 5. At the end of Part 4 we were talking about the bicycle wheel with a rope tied to one end of its axle and also tied to a rafter. It was on the back porch. You can see that bicycle wheel if you go to Gyroscopic Precession Part 1. Let's say this bicycle wheel is a 26-inch bicycle wheel, and let's say it has 2 kilograms of mass. So most of the mass is in the tire tube and rim. The mass of the spokes and bearings is relatively insignificant. So let's say its radius of gyration is 13 inches. 13 inches is 33 centimeters. So the moment of inertia, let's see, okay, 13 inches is 33 centimeters, so the moment of inertia, I, is equal to mass times the radius of gyration squared. So the mass is 2 kilograms, radius of gyration is 33 centimeters, which is 0.33 meters. And all that gets squared, so 0.33 times 0.33 times 2 gives us 0.22 kilogram meter squared. Okay, let's say the wheel is spinning 4 revolutions per second. This would be 4 times 2 pi radians per second. So its angular velocity would be 4 times 2 pi per second, which is about 25 radians per second. Okay, we use the term omega sub r to denote the rolling rate of our wheel, the number of times. That's the rate at which the wheel is rotating around its axle. The angular momentum, L, of the wheel is the moment of inertia, I, times the angular velocity, okay, omega sub r, which is, okay, our angular velocity was 25 per second. Our moment of inertia was 0.22 kilogram meter squared. So L equals that times that, which is that. Multiply it out and you get 5.5 kilogram meter squared, let's see, per second. If our rope is tied 2 inches away from the wheel's center of gravity, the gyroscopic torque that is applied to our rotating wheel is the weight of the wheel times 2 inches. The weight of the wheel is 2 kilograms times 9.8 meters per second squared, or mass times the acceleration due to gravity, which is 19.6 kilogram meters per second squared. 2 inches equals 5.08 centimeters. So the gyroscopic torque, well, 5.08 centimeters is 0.0508 meters. So our gyroscopic torque is 19.6 kilogram meters per second squared times 0.0508 meters. So we have kilogram meters times meters, which is kilogram meter squared, divided by a second squared. So kilogram meter squared per second squared, which is a Newton meter. A Newton is a kilogram meter per second squared. So a kilogram meter per second squared times a meter is a kilogram meter squared per second squared. Gyroscopic torque, by definition, is also equal to the angular momentum times the precession rate. Okay, here's our angular momentum, L. Here's an omega with a P by it. See our omega with a little R by it. That was the rotation rate. That's a real fast rate. That's the rate that the wheel's going round and round on its axle. Here's the axle. If the axle is horizontal and the wheel's going round and round it this way, that's the rotation rate. That omega means angular velocity. That little r means the velocity that's going around its axle. This omega p, that's the velocity that the wheel's precessing. Let's say here's the wheel doing this, but it's also spinning around like this. Well, the rate around this way, that's what omega sub p is, the precession rate. So don't confuse it with omega sub r. Okay, so torque equals the angular momentum times precession rate. Okay, which means our precession rate will equal our torque divided by our angular momentum. Let's see, which is what we have here. Okay, T over L, and our torque was 1 Newton meter, 1 kilogram meter squared per second squared. That's what a Newton meter is. And our angular momentum was 5.5 kilogram meter squared per second. So our precession rate is 1 divided by 5.5, which is 0.18. And you have kilogram meter squared per second squared divided by kilogram meter squared per second. So if you're going to divide by all this, that's the same as multiplying by flip-flopping it, putting seconds on top, kilogram meter squared on the bottom. Kilogram meter squared would cancel out. The seconds on top would cancel out with one of the seconds here, seconds squared, so you'd still be left with per second. That's why our answer, our precession rate, is 0.18 per second. That's radians per second. Radians are dimensionless. When we say our precession rate is 0.18 per second, we're implying 0.18 radians per second. Okay, a radian, so that's what our bicycle wheel should precess. That's the rate that it should go if it has a mass of 2 kilograms, if it's spinning around 4 revolutions per second, if the radius of gyration is really 13 inches. Okay, a radian is about 57 degrees, so our precession rate is about 10 degrees per second. So it should take 36 seconds for a wheel to precess a full circle. Remember our bicycle wheel from part 1 of gyroscopic precession. If it indeed has a mass of 2 kilograms, if its radius of gyration is 13 inches, and if it's going around 4 revolutions per second or 25 radians per second, then it ought to take about 36 seconds to precess. So 1000, 1001, 1002, 1003, 1004, 1005, 1006, 7, 1008, 1009, 1010, 1011, 1012, 13, 14. About 14 seconds it takes to go to precess 1/2 of a revolution. So about 28 seconds is what it would do for a whole one at that initial speed. So it's precessing a little faster than we figured it would, which means our radius of gyration may not be all the way out to there, it may only be to there. And it may not be going, well, I don't think it's going 4 revolutions per second now, it may not have been going that to begin with. But we're in the ballpark, so apparently the math works out and the formulas are putting us close to where we ought to be. Now that we understand the theory of gyroscopic precession, let's use this knowledge to solve a practical problem. Specifically, let's figure out whether or not the propeller on my steel stork is going to stay with the rest of the airplane or go flying off by itself. You can see the video of the maiden flight of this airplane on YouTube if you search for 20 seconds over Reidsville. So we saw with our bicycle wheel hanging by an off-center rope tied to the axle that torque applied to a rotating body causes precession. Conversely, forcing a rotating body out of its plane of rotation and into a different plane of rotation, not parallel to the original plane, causes a bending moment on the shaft that is used to change the rotating body's plane. This is a 3/4 inch shaft hooking to the propeller. This is a belt here turning a pulley. The engine's down there. That 1 inch hole in the center of the propeller should have told me something. But anyway, that 3/4 inch shaft came with the snowmobile that this engine and clutch came with. So I figured, well, I'll be able to take the greatest torque that the snowmobile engine puts on it. And since my belt out here is not at the tightest place, it won't be putting even that much torque. But I didn't even think about gyroscopic precession. So now we're going to take a look at it and see what the deal is. Okay, according to the ultralightnews.ca website, a 60 by 30 wooden propeller built by Tennessee Propellers, that's what this is. See, it's 60 inches from that tip to the other tip at the other end, which means 30-inch radius. 60 by 30, and that 30 number means when that tip goes around in a whole circle, if it goes at a 0-degree angle of attack, it will go 30 inches forward. Airplanes don't really go 30 inches every revolution. They generally go about 79% of that, but that's what that 30 means. That's the pitch distance. But anyway, according to ultralightnews.ca, that's CA as in Charlie Alpha, that website, a 60 by 30 wooden propeller built by Tennessee Propellers weighs 3.5 pounds. This means its mass is 3.5 divided by 2.2 because there are 2.2 pounds to a kilogram. So this propeller has a mass of 1.6 kilograms. If all the mass of the propeller were at the tip here, the radius of gyration would be equal to the radius of the propeller, 30 inches. But this is obviously not the case. The propeller gets pretty thin toward the tip. Most of the mass is closer to the center. See how thick the wood is up there close to where the propeller shaft hooks in, and how it gets thinner and thinner toward the end? Okay, if the propeller were shaped like a slice of pie, with its chord increasing from center to tip, okay, and its thickness remaining the same from center to tip, its radius of gyration would be 1 over the square root of 2, or 70.7% of the radius, which would be 21 inches. But that's not the case. This propeller isn't shaped like a piece of pie. It's bigger toward the center than it is toward the tip. A piece of pie is small at the center and real wide at the tip, where all the crust is. Okay. Our propeller's mass becomes less going from the center to the tip. Even though the mass toward the tip is less than the mass at the center, this far away mass causes the radius of gyration to be more toward the tip. Remember that the moment of inertia is the sum of all the increments of mass multiplied times the square of their distances from the rotational axis. So the mass that is far away from the axis contributes more toward the moment of inertia than does the mass at the center of the propeller. And the closer a rotational body's mass is to the radius of the body, the closer the radius of gyration is to the body's radius. Analyzing the propeller sliver by sliver from center to tip would give the most accurate estimation of the moment of inertia and consequently the radius of gyration. The website supercoolprops.com and some other websites say that the radius of gyration of a propeller is 55% of the way from the center to the tip. So the radius of gyration of this one would be 55 times, or 0.55 times 30, which would be 16.5 inches, and we're about out of time. We'll jump on this in the next section.